check that out. It's due on Wednesday. And thank you all for telling me your homework percentages. I got all of those, so that is settled. All right. So last time we were discussing the intermediate value theorem, and I gave you some kind of very half-baked story about the wobbly table. I've been thinking about it ever since, and I want to tell you the real story this time. This is not incredibly important, but you can amaze your friends with this fact about wobbly tables. So I'm going to start a new paper here. Intermediate value theorem and wobbly tables. She's not into the wobbly table. That's all right. So the situation, it turns out, is kind of complicated. Like, not really mathematically complicated, but it's a little difficult to explain. And I actually have been over the past couple days, I've been thinking over in my head what's the best way to explain this. And I was I tried to get here a few minutes early to set up all my screens and that, but I was a little later today because I was trying to explain to one of the other professors about the wobbly table. Because I'm still not satisfied with, I feel like maybe I'm still not doing a great job making it clear, and I want to explain as best as I can. Anyway, here's the idea. You have a square table which has even legs. So 4 legs, on each edge of each corner of the square, and you assume that the table has even legs. So I'm going to try and draw. I'm going to draw a little diagram here. Square table with even legs. They all have the same length. It's wobbling because the ground is uneven. All right. So actually, the table is kind of like these chairs that you're sitting on. They have 4 legs, which are, I suppose, the same length. So it's a square table. It has even legs, but it wobbles because the ground is uneven. So you have to imagine, like, you put a rigid 4-legged table on the ground outside or something. You don't really expect that it's going to be balanced perfectly because the ground is uneven. All right. And I'm going to try to explain in a few moments using the intermediate value theorem. Remember, the intermediate value theorem just says if you have a continuous function and it has one value somewhere and another value somewhere else, then it has to achieve all the values in between. And one very specific application of this is if your function is positive somewhere and it's 0 somewhere else. Sorry, if it's positive somewhere and it's negative somewhere else, it means it has to be 0 somewhere in between. All right, this is the intermediate value theorem. So I'm going to try to explain how if your square table is wobbling, you can balance it. First of all, it is possible to balance it. And the way you can do this is just by turning the table. And as you turn it, it will naturally sort of find a spot where it balances. All right? This is what I'm going to try to explain to you in just a few moments. And you can explain to your friends too. It's not really mathematically complicated, but the explanation is, for my taste, a little convoluted. But I'm doing my best here. Okay, so I'm going to try to draw a little diagram here. You don't have to draw a diagram when you're explaining this to your friends at dinner. Here's my table, right? It has 4 legs. This is like a top view of the table. And let's imagine the legs are sort of sticking out so that you can see them in my diagram. Now, when I say it wobbles, what that means, if you think about it, I mean like the table does like this, right? What that means geometrically is actually 2 of the legs are touching the ground, and the other 2 are kind of floating, right? That's what it means for a 4-legged table to wobble. So just for my diagram, let's say these 2 are touching the ground. Like 2 opposite legs will be touching, and the other 2 legs, you could somehow balance it, even though it's wobbling. You could somehow balance it in the middle so the other 2 are sort of floating at an equal distance on either side above the ground, okay? So these are touching, this one and this one. And the other 2 others are floating, right? And that's why it wobbles. since the table is perfectly even, what this means, I suppose, is that the ground is uneven, and specifically it's uneven in such a way that the two touching ones are kind of on higher ground, and the two floating ones are standing above lower ground, right? That's why they are floating, and why the other ones are touching. Okay, so what we have here is sort of high ground here, and low ground here, and low ground here, right? That's what the ground must look like, at least nearby those points, in order for this scenario to be occurring. Okay? This is the table, I imagine, like when we start off, it looks like that. All right, I'm going to call this like the before picture because I'm going to describe how you can move the table to another position. All right? What I'm going to do to move it, this is simple. I'm just going to pick the table off the ground temporarily, turn it by 90 degrees, let's say clockwise, and then shove it back down on the ground. So I turn it. Now it's a square, so it looks the same, only these ones now, they're here, right? This is the after picture. I rotate 90 degrees, pi over 2 radians, if you like, clockwise. It doesn't matter, actually, since the symmetry. All right? And I'm going to shove it down so that the same ones which were touching before are touching again, touching the ground. Shove it down so the same ones touch the ground. All right. I would like to ask you, what is the position of the other two legs now? Where are they? Are they still floating above the ground or what? Anybody have any thoughts about this? I've turned the table and then forcibly jammed the two that used to be down. They are all the way down touching the ground. Any thoughts about the other two legs? They are touching as well. I think actually, that's true. I think we can say a little bit more than that. Anybody have any feelings about this? Yeah, they would be like driven deep into the ground in this configuration. That's because, remember what I said before, up top and on the bottom, this is high ground, whereas this over here is lower ground, right? So after you turn the table and then jam it down so that these guys are touching, that means these guys will now be buried into the ground, all right? If that's permissible. You have to imagine this is like soft ground, all right? The same ones touch the ground. The others will be buried, all right? Down deep into the ground. So they are no longer floating above the ground. They're now sort of sunken beneath the ground, all right? Remember the intermediate value theorem? Eventually I'm going to say something about if something begins being positive and then later on is negative, that means at some point in between it had to be zero. Anyone connect the dots here? You see something which was positive and then is negative, or the other way around? Anyone still with us here? I think before you move the table, if you look at the height of those other two legs that are not touching, how far off the ground are these guys? They are floating above the ground before you move the table. After the movement, they are now sunken into the ground. And so if you imagine, instead of me picking the table up and turning it, let's just say I leave it where it is and turn it in place. Well, if I'm going to turn it in place, and those two legs, they begin floating above and they end up sunken under, that means at some point during the turn, they have to touch the ground exactly, right? If they start above the ground and they end below the ground. There has to be some point while I'm turning it where the two legs touch the ground. And in fact, the two legs will touch the ground at the same time if while I'm turning it, I'm also constantly angling it so that they're sort of balanced out. These two wobbly ones are of an equal height above the ground. I can do that while I turn. And then there will be a moment when they both touch the ground exactly. Are you satisfied? This is kind of complicated, and every time I explain it, I feel like there must be some simpler scenario to describe the same thing. Well, I can't think of any simpler way to describe it. So I would invite you to talk to your 8-year-old little brother, see if you can convince them of this fact. All right? Any questions about that? Was it worth it? I don't know. It took about 10 minutes. All right, this is the intermediate value theorem applied to wobbly tables. Not convinced it was worth it, but I mentioned it last time and I figured I had to follow through. Any thoughts about that? questions? All right, let's continue. So I had one more sort of real conventional mathematical example about the intermediate value theorem, and then I want to go on to the next chapter. You can use the intermediate value theorem to find particular solutions to equations. Like last time, remember we found, last time we didn't quite find a value, but we showed, this was what we did at the very end last time. We showed there is some x with sine of x equals 0.867539, remember that? You can use the intermediate value theorem to find or to demonstrate that particular values must exist. Actually, an interesting subtlety is we never actually found that value x. I didn't tell you what the value of x is. We just sort of said, well, on the graph of sine x, here the y value is 0, and here the y value is 1, and so in between it must be that other number, even though you don't actually know where the x is, which makes the sine of x equal to that other thing. We demonstrate that there is a solution, though. So anyway, the intermediate value theorem can demonstrate solutions to equations. It doesn't really tell you what the solution is. It just, you can use it to explain that the solution exists. Demonstrate solutions to equations. But it doesn't actually find the value for you. It doesn't find the solution, right? This is an interesting kind of a thing. This is what mathematicians call this a non-constructive technique, in that it tells you that the x exists, but it doesn't actually tell you what it is, right? But for many purposes, this is sort of good enough. If you're an engineer, typically you want to know what the value is, not just that it exists. That's usually not good enough. You want to know what it is. But mathematicians often are interested in this kind of existence thing, even if you don't know what the value is. Do you want to hear a math joke about non-constructive solutions? So here's a math joke. You know, typical math jokes, I in general think that all math jokes are stupid, but and this is also stupid. But typical math joke. This is just that kind of joke where like something happens 3 times, and the first 2 times it's more or less ordinary, and the third time it's weird, and that's why it's funny. You know what I'm talking about? This is the structure of the joke. I'm telling you the structure of the joke first. So the joke is, let's say there's a chemist and an engineer and a mathematician, and the chemist is staying in a hotel. And wakes up in the middle of the night and finds that the bed is on fire, like the bed near their feet or something. And the chemist wakes up and sees next to them is the ice bucket, which is full of ice. So they dump the ice bucket onto the fire. Fire goes out, everything's fine, go back to sleep. The engineer is in the same scenario somehow. They wake up in the middle of the night and the bed is on fire. The engineer finds a pile of the blankets that they're not using, and they kind of like cover up, smother the fire. Fire goes out. The engineer is satisfied, goes back to sleep. The mathematician wakes up in the middle of the night, the bed is on fire. The mathematician sees the ice bucket full of ice, looks over, sees the blanket. The mathematician says, okay, a solution exists, and then goes back to sleep. You get it? They didn't put out the fire. Because all they care about is that there is a solution. They don't actually do it. That's why it's funny. I'm explaining to you why it's funny. All right. That's my math joke about non-constructive. Sometimes mathematicians, they only care about whether the solution exists or not just what it is. All right? Excellent. I think part of why I don't like math jokes is because they usually as a joke, it's not funny. The only reason it seems funny is because you get it. Like you understand what a non-constructive thing is, and that's why you get it, and you laugh because you are so pleased with yourself that I understood that joke, and my my stupid brother probably wouldn't understand that joke because they don't know math the way I do. I don't know, there's some kind of elitism in math jokes that is distasteful to me. Anyway, anybody have any comments about that? No, I don't think so. So let's try just one more example of this, and then, like I said, I want to go on to something else. So the intermediate value theorem you can use to demonstrate that certain equations have solutions. We did one last time. Let's just do another one. How about, let's show that, how about this? X cubed plus 5x minus 100 has a root. All right? This is a polynomial, so it is a continuous function, right? Now, the word root used in this context, root here, it just means some value x with f of x equals 0. This actually doesn't really have anything to do with square roots or other kinds of cube roots or whatever. The word root in this context, the root of an equation just means some value in the domain, which makes the equation equal to 0. All right, can we show that this has a root? My strategy, using the intermediate value theorem, to show that the value is sometimes 0. That's what this says. We have to show that the y value does equal 0 at some point. Using the intermediate value theorem, all you got to do is show that there is some y value that's positive and some other y value that's negative. And that means automatically in between there must be a y value that's 0. So that's my strategy. So I'm going to find some x with f of x positive and some x with f of x negative, right? And then by the intermediate value theorem, this automatically will mean that the f of x is 0 at some point, because it's going to be, if it's going to be positive and then negative, it has to be 0 in between, all right? And for this, we don't really know anything special about this function. We basically just have to guess this. So there's plenty of us here. We're all smart math students. Anybody want to guess? Can you guess the value of x where the value is positive or perhaps negative? What do you think? Sure.
At 100, it's positive.
Okay, yeah, if I use x equals 100, say, I mean, I suppose you could use your calculator for this, but I can do this in my head, I think. For x equals 100, what do I get? I get 100 cubed plus 5 times 100 minus 100. What is that? It's a really big positive number, right? Whatever that is. This is positive. All right. Can anyone find a value of x where you get a negative? Again, you just sort of invent something. Yeah. 2. Okay. I would have accepted 0 as the answer. In my opinion, 0 is the most sensible thing to do. But yeah, 2. If you plug in x equals 2, you get 8 minus 10 minus 100. That's definitely negative, right? I'm going to use his suggestion. You get 2 cubed plus 5 times 2 minus 100. This is negative. Negative. All right? And so it means that the function has to be 0 at some point in between. And we can be slightly specific about when is it going to be 0. So that means that f of x equals 0 for some x. Actually, we can say it has to be some value between 2 and 100, right? Because at 2, the thing is negative, and at 100, the thing is positive. And so that means there must be some value between 2 and 100, right? And that's really all I want to say about that. This is a traditional usage of the intermediate value theorem. In fact, you can, if for some reason you really wanted to know what the value of x was, you could try to narrow this down by plugging some number in between. Like, for example, if I plug 5, what does that give me? That's 5 cubed plus 5 times 5 minus 100. This is 125 plus 25 minus 100. That's positive, right? This is 50. So actually this allows you to narrow it down. Remember I said before when you use x equals 2 it's negative, but now I decided when I use 5 it's positive. So that means actually f of x equals 0 for x in the interval from 2 actually to 5. This is a much narrower band, but we have now more information about when the root occurs. All right, and if you could, if you want to, keep on narrowing this down. Like you could try out 4, see if that's positive or negative, and this will allow you to sort of continue to narrow the interval down to get closer and closer to the real value. You'll never be able to compute the exact value in this way, but you could, if you keep on doing this, get closer and closer to the true value of x. I'm not going to get into it. But. All right. Any thoughts about that? This is the intermediate value theorem. More about the intermediate value theorem you ever wanted to know. Okay, let's go on to the next bit then. This is actually the end of chapter 1 in the book. Chapter 1 is all about sort of review topics and then the limit, right? Chapter 2 is all about the derivative, which is the first sort of big major calculus kind of topic. I mean, limits are a big topic in calculus, but actually, when it comes to using calculus in the real world, the derivative is the thing that people use most often. Really, it's the derivative and the integral, which are the two major topics for this class and the next, calc. This is calc 1, but calc 2 is also about mostly the integral. So the derivative. This is something that I kind of talked vaguely about before we talked about limits in detail. We're going to go back to this concept about the slope of the tangent line, right? That's what I talked about. That's called the derivative. And it is, I will say, the fundamental measure of how fast a function is changing is the derivative. There are other ways you can measure how fast a function changes, but for basically all useful purposes, the derivative is what you want to talk about if you're asking how fast something is changing. It is the fundamental measure of how a function is changing at a point, at a moment, right? And it is the slope of the tangent line. All right, so on a picture, you have your graph here. Maybe it looks like that. If I want to know how fast is a function changing right there, the way to measure that is by looking at the slope of the tangent line, which I will say something like this straight line here, right? And we discussed this in vague terms a couple weeks ago. We're going to get right down to it this time, though. Some real details here. All right, where this, let's just label that point. I'll call this A here. This, of course, is f of a over here. All right. The slope of that line describes the rise over the run. Of course, that means how fast the y is going to change divided by how fast the x is changing, right? It's that slope, that little rise over run. There are several different names we use for this number. It is a number because it's just the slope of that line. Different names for this. There are different ways that we can describe it. First of all, it's the slope of the tangent line. These are all, I'm going to write a bunch of synonyms here. Slope of the tangent line at x equal a. All right, that's what it means. But this is the same as we also call this the derivative of f of x at x equal a. All right, if my function is called f of x. So the slope of the tangent line is also called the derivative. Those are like synonyms. This is also called the instantaneous rate of change. The instantaneous rate of change at x equal a. That language is meant to contrast with the average rate of change, which is something that you did on your homeworks last week, where you were given two separate points and you measure the average change from this point to that point by doing a little f of b minus f of a over b minus a, right? This is the instantaneous rate of change at just one point in particular. This is also written in notation like this. F prime of x, that little apostrophe there, is very important. Don't leave it out. I mean, without that, it's just f of x, which is the y value. When you put the prime there, you are talking about something very different. It is the slope of the tangent line at a particular point. Sorry, not x. I meant to say a there. If I'm talking specifically about the derivative at this point a, that's written as f prime of a. F prime of x is the derivative as a whole function. Of course, they're related. And then there's one other way that this is written. Well, there's a few others, but here's one other. This is a little weird. Actually, I'm not going to write this for now. You know where I'm going with this probably if you've seen that before, but I don't want to get into it for the moment. There's another way of writing the derivative, which is with the d's. We'll talk about it eventually. All right? Anyway, all of these things represent the slope of the tangent line. There are different ways that we say them, but they all mean the same thing. Let's talk about how you actually find that slope. I think I said, a couple weeks ago, this was a major unsolved problem in mathematics for many centuries. The question of, if I give you a general function, can you tell me what the slope is at a particular point? Now we know how to do this, and we will all, if you don't already know, you're going to know real soon. But there was most of human history, people wanted to do this but didn't really understand how to do it. How to find the slope? The idea is, I'm going to draw another graph here. If I have some curve like this maybe, and I want to know what's the slope right at A, the concept is you measure the average slope between 2 points, which is easy to do. There's a simple formula for that. That would be this. That would be this slope here, right? Measure the average slope, or the average rate of change, to a nearby point, which is the b, right? That will not be exactly equal to the tangent slope, which is this one here. This is the tangent, not very, something like that, right? Now on this picture, they don't really look all that close. Here's my other point, which I'm going to call b. If I measure the average slope from A to B, that's not the same as the tangent slope. But if you can imagine this point over here, B, was growing closer and closer to A, well then this black line slope would actually approach the blue line slope eventually in the limit. All right? This is the key idea which people figured out. The way to find that tangent slope is by doing a limit of the average slopes. So the idea is you measure the average slope to a nearby point called B, and then do the limit as B approaches A. All right? You take the limit as that second point moves towards the A, moves to the left. And then that black line in the limit will end up having the same slope as the blue line. This is how you find the slope of the blue line, by actually figuring out that limit. So the tangent, I will write this as a formula. F prime of A, that means the slope of the tangent line at A is equal to lim B approaches A, f of B minus f of A divided by B minus A. All right? And this is something you can actually work out. You can actually compute the value of this limit. Let's try a specific example. That is the formula we're going to use. Let's say find the slope of f of x equal f squared minus x at the point a equals 1. All right? sometimes you'll see this. I said the slope of the function rather than, I didn't say the slope of the tangent line. When you say the slope of a curve, that it is implied. What you mean by that is the slope of the tangent line. That's the only thing that the slope of the curve could possibly mean, is the slope of the tangent line. All right, so I'm going to use that formula that you see up top here. I'm going to plug in A equals 1 in that formula, right? And here's a trick question. What am I going to plug in for B? The answer is you don't plug something in for B. B is the variable which you are going to take the limit with. So I'm going to use this formula up here. I use A equals 1. And it says lim B goes to 1. All the A's I'm going to write as 1. F of B minus F of 1 divided by B minus 1, right? And we're going to see if we can actually do this. What do you do with the f's? Well, this f refers to this function. So when it says, f of x is x squared minus x. When it says f of b, that's, I guess, b squared minus b, right? You plug b in instead of x. That's what f of b means. So it says lim b goes to 1. B squared minus b minus, what is f of 1? Can anybody tell me what's f of 1 in this case? 0. I think I heard a whisper in the wind. It's 0. Yeah. If I plug f of 1 means you go here and you plug 1 into the function. 1 squared minus 1 is 0. That's a 0. Okay, and then on the bottom, b minus 1. All right? Just to simplify a little bit, well, 1 squared minus 1 is 0. So this really says lim b goes to 1 of b squared minus b over b minus 1, right? What do you think? What can we do with this? I mean, eventually we're going to take the limit by plugging b equals 1, right? Because that's what the lim says. But actually, if you do that right now, you'll get 0 over 0, which means you need to somehow simplify more. Anybody have a suggestion? How can we simplify that? Perhaps factor something or something? Yeah, what do you think? Yeah, in the top, you can factor b out. B minus 1, right? Over b minus 1. And now you can cancel those b minus 1s like so. So this is, we're almost done here. Lim b goes to 1. B, right? The answer is 1. Yeah, showing me the finger. 1. All right, that's the slope. So apparently, I mean, I didn't draw the picture, but x squared minus x, it looks like a parabola, sort of like that. And apparently the slope right there is 1. It looks kind of reasonable on my picture. All right, slope of 1, of course, is a 45-degree angle line going up. All right, any thoughts about this? Any questions about that? This is finding the slope of the tangent line. We just did it. This is like, People tried for centuries to do this and didn't know how to do it. We just did it. This particular example is a parabola. Actually, it was known how to do this for parabolas. They had like special tricks for doing every different kind of function. They learned like custom tricks for parabolas or for cubics. This basic structure, though, doing it as a limit, suffices to compute any of those using the same methods, really. All right. This formula right here, this is the formula for the derivative, the slope of the tangent line. Actually, that one, which we just did, is not the formula that we're usually going to use. If you've seen this before, you might have learned it, slightly different looking formula. This one, I mean, it's not wrong, but I find it slightly easier to look at it in this way. So another version of the same thing. And this is what I'm about to write is the formula that we're usually going to use. If you have your function, say, instead of choosing two different points, A and B, I'm going to choose my A, like A is where I want to find the tangent. Rather than choosing some other point B, I'm going to choose some distance here. This distance, in some textbooks, they call it delta x. In our book, it's just called h. All right? I'm going to choose this distance h and then this point, so this one is A, and then if I move over to the right by a distance of h, that point, I guess, its value will be A plus h, right? Just because it's some point to the right of A by that distance h. And then these y values, of course, this is f of A, and this y value is f of A plus h, all right? And so this slope, the average slope here, is now, when I do the average slope formula, I'm going to get the first y value minus the second y value, and then divided by the difference between the x values, which in this case is just h. H is the distance between those two x values. All right? This usually turns out to be an easier formula to use. And in this case, remember, we still want to do a limit so that this point goes and approaches A in the limit. And the way to make that limit happen is just to make this distance h go to 0. So the formula is this. Lim h goes to 0 of that business. This is what we are typically going to use to find the derivative at a point. So I'm going to put that in the box and say you definitely need to remember this formula. I would expect you to know this on a test or something. You're going to use it fairly often, so I don't think you'll ever have to like sit down and forcibly memorize it. After you use it a few times, you will naturally remember it. All right, this is a formula for the tangent, the slope of the tangent line. If you prefer that other one, you can use that other one, but I find this one to be a little bit easier to handle. Yeah. Okay, so if you've already learned about the derivative, you probably learned that there is a truly awesome trick for doing the derivative of polynomials. It is like, if you're not aware of this trick, this is like a life-changing trick. It is the greatest thing in the world. So his question was, can I just do it that way instead? Because I don't want to do all this nonsense if I can do that awesome trick. The answer is, I want you to do all this nonsense, at least for the next few days, because it's important that I want us to really sort of live and breathe the slope here, right? This slope is expressed by this limit. If you use the trick all the time, which you should in general, but for now we're not going to, but the trick really obscures the details of, or it totally obscures the idea of what you're doing. When you learn the trick, actually, the procedure when you're using the tricks has nothing to do with slopes of anything. It doesn't resemble it at all. So, what I'm trying to say is, for now, we're going to use the definition using the limit, but soon enough, we're going to learn some tricks which make this seem like the hard way. All right? Great. Let's, so I want to do a couple examples using this formula to find the slope of the tangent. This is one of those things that, like, if you, sometimes I wonder to myself, if I were to, if I had a time machine and I could go back in time to the deep past and see the people and tell them I'm from the future, I wonder how I could convince those people that I was really from the future. Like, is there knowledge or skills that I have that they would recognize as being useful knowledge or skills? I think some things, a lot of my modern knowledge of science would be useless, either useless or unbelievable to them. If I said, you think the sun goes around the earth, but actually the earth goes around the sun. They would say, oh yeah, prove it. And I would not know what to say next. I think there are very few skills that would be transferable. But I think if there were mathematicians among them, I could dazzle them with my ability to find the slope of the tangent line. This is something that some people in the world wanted to know how to do, but they didn't know how to do it. Anyway, let's try the same. Let's do this same example, but using this version of the formula in the box. So I will refresh our memory. It was f of x is x squared minus x, and I want to find the slope at a equals 1. All right? And the answer was 1. when we did it the other way. That's where it was, right? Yeah, at a equals 1. Okay, I'm going to use this formula, though, the one which you see presently in the box. So it is f prime of 1, that means the slope of the tangent line when x equals 1, is, I'm going to write this, lim h goes to 0, f of 1 plus h, I use a equals 1, minus f of 1, divided by h. All right? We're going to plug everything in, simplify as much as we can, eventually take the limit by plugging in h equals 0. Let's see how we do. What do you think? Anyone want to say, what should I do with f of 1 plus h? This will get slightly more complicated when you try to actually plug this in, but somebody want to shout it out? What is f of 1 plus h? It means I go over here and I plug in, instead of x, I use 1 plus h. This may be the hardest step. It's not that hard if you know what you're doing. Yeah. Yeah, right. 1 plus h squared minus 1 plus h. Yeah, that is what you get when you do f of 1 plus h. You go up here and you replace every x by 1 plus h. So it said x squared, I say 1 plus h squared. And then it said minus x, I say minus 1 plus h. Make sure you put those parentheses in the right spots. They matter. And then minus f of 1. That means you go back to the original function and you plug in 1 instead of x. So I say 1 squared minus 1, which that's going to be 0. All right? Make sure you put those parentheses. I know I've heard on the playground that there are some parentheses haters out there. Some people just don't like writing the parentheses. And I say, hey, what about the parentheses? And they're like, I don't need the parentheses. I just remember all the parentheses. My response is, well, all right. It's a free country, but you are liable to mess it up if you don't write the parentheses. And if you don't write important parentheses in the answer, then you got the wrong answer. I consider it a personal choice if you just decide not to write the parentheses inside the intermediate steps, but you are likely to screw it up. I feel the same way if I meet somebody who writes me an email but leaves out all the vowels. I'd say, why didn't you put the vowels in there? And they're like, well, I knew what I meant. All right. And I can more or less figure out what you meant too, I guess. But come on now. Put the parentheses in there. It's kind of we live in a society kind of thing. Okay. We need to somehow expand this thing in the hopes of simplifying it and eventually taking the limit. So what we should do is, I would say, do the FOIL here. 1 plus h gets squared. And then I'm going to distribute a minus sign here. So I do the FOIL on the 1 plus h. I get 1 plus 2h plus h squared. All right? That's the 1 plus h squared. And then it says minus 1 plus h. I'm going to distribute the minus 1 minus h. If you didn't put those parentheses, you might have forgotten to distribute the minus sign, and this actually will affect the answer, that minus sign right there. Will mess up the answer if you did it wrong. Okay, and then this, 1 squared minus 1, if you want, you can distribute the minus sign, or you can just add up the numbers inside the parentheses, which is how I usually do it. 1 minus 1 is 0. So actually that part is just 0. So I'm not even going to write. All right. What can we do with that? Try to simplify some more. How do we simplify that? The ones will cancel. I think I heard somebody say something, although I have no idea what she said, but I'm going to guess that she said, you can cancel the ones here, right? I got a plus 1 and a minus 1, so those can go away. And then you can also add together 2h here and a minus h. So this will add up and you get just 1h. So this is going to be lim h goes to 0. H plus h squared divided by h. All right, the 1 and the minus 1 canceled. The 2h subtracts h, and I end up with just 1h. And now, actually, this now looks the same as the one we did it with the other formula, although that one had b's. I'm going to factor the h on top, h, and then 1 plus h divided by h, right? Cancel the h's, and plug in h equals 0. I get 1 plus 0, which is 1. All right? So we did get the same answer as expected when we used the other formula. All right? I don't know if you like this better than the thing with the a's and the b's. Like I said before, you can do it either way. I am basically always going to do it this way. And after next week, I'm always going to do it using the tricks, which are much better than this. All right? Any questions about that one? Let's just do one more. I think that might do us for the day. How about, sometimes, so remember this derivative thing that we just did? It tells you the slope of the tangent line. Sometimes we want to actually know what the whole line is, like the equation of the tangent line. Let's try one like that. How about find the equation of the tangent line. Sorry, my handwriting is sometimes good. Find the equation of the tangent line for y equals square root x at x equals 4. All right. Square root x. You know, the graph here, it's not really useful to think about the graph, but just to remind everybody what we're talking about, the graph of the square root looks like that, and then at x equals 4 would be here. I suppose the y value there would be 2, right? So the slope I'm talking about is that. All right, how do we do it? So, okay, I'm asking for the equation of the tangent line. The typical strategy you use for this is we're going to use the point-slope form of a line. And I hope you remember the point-slope form. And the hardest thing about this problem is going to be finding the slope. That's how we use the derivative. The rest of it is just a matter of remembering how to use the point-slope form. But the point-slope form looks like y minus some specific point equals m times x minus some other specific point, where the x0 and the y0 are the x and y coordinates of one specific point that you know is on the line. And the m is the slope at that point. All right. So I'm going to use, as for my point, I'm going to use, you know, this point right here, which is where we're talking about. This value is going to be x equals 4, y equals 2. So eventually I'm going to use a 2 here and a 4 here. But the more interesting thing is how to find the m, and that is what requires the derivative. So that's the bulk of the work for this problem is the m. All right. Once we find the m, then we just plug everything into the point-slope form and we'll be done with it. For the m, we use this formula for the derivative, right? F prime, in this case, it's f prime of 4. And I'll go lim, h goes to 0, f of, remember it's f of a plus h minus f of a divided by h, where the a in this example is 4. So I'm going to say f of 4 plus h minus f of 4 divided by h, like that. All right, this is the formula that was in the box before. I don't think we care about the picture anymore. All right, we do care about the function though. The function is here, the square root of x. So what do we get? F of 4 plus h. What do you think? Anybody shout out? What do we get when we plug in 4 plus h to f? As usual, it means you go back to the formula for f and you replace x's with 4 plus h. What do you think? Yeah, square root of 4 plus h. Great. All right, you replace the x's up here with 4 plus h. Okay, minus. Next comes f of 4. That's a little easier, I think. You go up here and you just plug in 4 to the function. Instead of x, you replace it with a 4. You get square root of 4, which is 2, of course. I'm going to write it like that just so we're clear. All right, so this is square root 4 plus h minus 2, right? By the way, I write out a lot of intermediate steps. That's just to make everything clear. When you're doing this on your homework or whatever, if you want to do some steps in your head, that's fine with me. Okay, what can we do with this? You know, we intend to take the limit by plugging h equals 0, although if you did it at this point, you would get a 0 over 0. So what should we do instead? This is the point at which sometimes you go back and factor, but can't really factor here. Yeah.
Get the exact terminology, but we have to rationalize.
Yeah, you do that rationalizing trick that we did a few times. You did it on the homework, I know. You multiply here by, like basically that thing in the numerator with the square root, but instead of that minus 2, I'm going to use a plus 2. So it's going to go root 4 plus h plus 2 over root 4 plus h plus 2, right? This is the rationalizing trick. It does come in handy sometimes. So on the bottom, I'm going to get h times root 4 plus h plus 2. And actually, it's not helpful to distribute the h on the bottom. On the top, when we multiply those guys, remember what happens when you do this rationalized thing? You'll get the square of the first two things, which ends up just being 4 plus h, and then minus the last two things multiplied together, which ends up being 4, like that. So if you do the rationalized trick, this is what you end up with. You can cancel the 4's there, right? 4 plus h minus 4 will just be h on top. And then you can cancel the h on the top with that h on the bottom. This is why it's not helpful to distribute on the bottom. So I'm going to write out that intermediate step. I end up with this guy, and then the h on the top and the h on the bottom will cancel. Like so. And we get, what remains is just 1 over square root 4 plus h plus 2. And now, finally, we can do the limit by plugging in h equals 0. And what we get is 1 over square root 4 plus 2, which is 1 over 2 plus 2. 1/4 is the answer. So the slope of that line is apparently 1/4, which actually I think looks pretty good on my picture. That slope of this line here. 1/4 is like up 1 over 4, which looks like maybe that's accurate for this picture. All right, this is not quite the whole answer. Remember, the answer was, or the question was, find the equation of the tangent line. All of this was going to be plugged into the point slope form using the m, which we just found was 1/4. So my answer is, I'm going to remember this thing with the 2 and the 4. So back to the actual answer is this. But I used 2 and 4. So y minus 2 equals 1/4 x minus 4. All right? And this is the equation of that tangent line. If you like, you could rearrange this so that it looks like a standard, like mx plus b format. If you want to do that, it would say 1/4 x minus 1, if I distribute the 1/4 there, and then solve for y, 1/4 x plus 1. This is the equation of the tangent line. All right? And if you wanted to sort of check your answer here, you could just graph yourself, graph the square root function, and then graph this line. And if you did it all right, it should look like that picture I drew before. You should have the square root and this line touching it exactly at just one point. All right. Any questions about that one? I had one more kind of lengthy example to do. I think I'm going to leave that for next time. I know everybody wants to get home. Watch the new My Little Pony movie. Just came out today. All right, have a good weekend.